Hello, my name is Aiko and welcome to my talk on artificial intelligence, or more like artificial stupidity. And what I'll be doing today is I'll be telling you a couple of stories. I'll be telling you stories about artificial intelligence, I'll be telling you stories about machine learning, and I'll be telling you stories about data. And some of those stories are success stories, but some of those are not. And we will in particular look at those who are not, and we will look at why they failed, and we will look at things how we can in the future prevent the same things from failing again. And when I say I'll be telling you stories, let's start with one of the greatest storytellers out there, which is Douglas Adams. And I'm sure some of you have read this book, The Hitchhiker's Guide to the Galaxy, which has brought us a couple of particularly famous memes, like the one that the answer to the question of life, the universe, and everything is 42, and that we should not panic. And has been particularly popular in the tech community. And one thing that is not as popular, but that Douglas Adams also introduced, is this Babel fish. It's this fictitious fish that lives somewhere in the universe, that is tiny, and if you can put that into your ear, and what this fish does is it picks up all the spoken languages around you and translates that into a language that you understand. So any language in the universe, it gets directly translated into a language that you understand if you have this fish in your ear. And obviously that is fictitious, and it's a crazy idea. It's a fantastic but a crazy idea, right? That would never work in real life. Now let me show you a little demo. Hallo und herzlich willkommen zu meinem Vortrag über künstliche Intelligenz. Now, if we look at this, right, this is almost as cool as putting a fish in your ear. I mean, admittedly, I still have to click that button, and we have to go to that website to translate it, and it doesn't. I could click this listen button and it would actually read it out, but I would still need to click it. But it's not quite there yet. It's not quite this Babel fish that you put into your ear. However, Google also sells these in-ear wireless headphones, and they use the same technology as the Google Translate page that we just saw. And they use the voice recognition. And what they do is, it is more or less the exact same thing as this Babel fish. Someone can speak something in a language that you don't understand. You still need a phone a little bit. But then the earphones do translate that and directly into your ear say the translation in, for example, English. So this fictitious fish, which sounded so absolutely amazing, right, is due to the use of AI and machine learning is almost already there. And that is one of the fantastic examples where AI and machine learning has definitely succeeded. And there are more examples. And this one in particular, I mean, the translation one is pretty good, but this one is life-changing, basically. Over the last couple of years, people have been developing image recognition systems for cancer. And in some cases, machine learning nowadays can predict cancer with a higher rate than human doctors can. So a couple of years ago, I think it started with breast cancer, and last year Google released a machine learning model that can, based on pictures that we can see here, for example, can predict that there are cancer cells more accurately than human doctors can. And I think that is something that is really impressive, and that is a great success story for machine learning and for artificial intelligence. But we all know, and especially if you think of the title of this talk, it doesn't always work that well, right? For example, this person on the very right is sending a tweet to Indigo, which is an Indian airline, and he's complaining about that his baggage went to Hyderabad while he was flying to Kolkata. And the response of Indigo, and I assume this is in AI, the response is, "We're glad to hear that." So obviously they didn't pick up on the the sarcastic tone that the user was using here. And in the middle, you can see a screenshot of someone contacting PayPal and mentioning that he got scammed, and PayPal's response is, great. So clearly there are a couple of cases where AI simply fails, and not even difficult cases, right? And this one is one of my favorite fails of AI. And if you speak Mandarin, you could already figure out what it says there and figure out what was going on. For everyone else, I give you a little bit of a backstory. In a couple of cities in China, they have cameras installed at zebra crossing, at pedestrian crossings, cross streets, and when there's a red light, these cameras record the person crossing the street at a red light. They record the person jaywalking, and what they then do is in this case, what you can see here is a big screen, and what happens is if you get caught jaywalking with the camera, they show your face and they zoom in on you, and they basically shame you and make everyone see that you jaywalked. And some other cities even have this system connected to WeChat Pay, where they record your face, they use image recognition, facial recognition, they figure out who you are, and when they know who you are, they know your bank account, they figure out your WeChat Pay wallet, and they immediately deduct the fine for jaywalking from your WeChat Pay account. Your WeChat wallet immediately gets deducted that fine. Right, and now with that background, if we look at this picture here, we can see this is not really a person crossing the street. What happened here is there's a bus which has the face of a person printed on it. In fact, this is the CEO of a company, and they're advertising with her on the bus. And the bus, like the pedestrian had a red light, and the bus drove by. So the camera was pointing at the bus, seeing the side of the bus, seeing the face, and recognizing, oh, there's a person crossing the street at a red light, and then showed that face, zoomed in on that face, and showed everyone, hey, this person just crossed the red light. And in fact, they even sent a message to this woman, which was a couple, like in a different city at that time. And when she got the message, hey, we just saw you jaywalking in that other city. And this is where, from a technical perspective, this is very interesting, right? Like having this facial recognition, having it connected to your bank account, more or less, is very interesting. From a different perspective, you could also say that if you let machine learning or AI decide whether you have committed a crime or not, is questionable, and this is a great example why it is questionable, because you can see that it also fails. We have seen other cases where machine learning fails, and you don't want to give it that much power if you can't be sure that it does not fail. So I've been talking about artificial intelligence and machine learning a lot. All of these terms have been hyped in the last couple of years, and lots of people are talking about them. And I think in the context of this talk, it would be good to have a common understanding of what, when I say these terms, what I mean by them. And we can start with artificial intelligence, and there's this definition that I really like, that comes from the Oxford dictionaries, which is, by the way, also the definition. If you type in Google, define artificial intelligence, you also get this particular definition. And this definition reads out as, artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. And the important thing to note here is that it does not talk about any technical approach. When we get to machine learning later, we'll talk about technical approach. Artificial intelligence is a very broad term describing anything that a computer does that you would think takes human intelligence to do. And the chess program is a good example, where if you play chess against a human, you would usually assume that person, or if a person can play chess, you would assume the person has some kind of level of intelligence. Now, if you think about how we would implement a chess program, like a computer to play chess, it could be a relatively simple approach, right? You could just write a program that looks at the current state and then brute forces all the possible moves and subsequent moves to see which set of moves arrives as the desired state, which is winning that chess match. And brute forcing and a couple of if-elses is not a very sophisticated technical approach. It would, however, fit into this definition of artificial intelligence. So, from my understanding and following this definition, artificial intelligence is a very broad term that just describes a use case where you would assume human intelligence is necessary done by a machine. Machine learning, on the other hand, is where it becomes interesting. Machine learning describes a technical approach to solving a problem. And in machine learning, the algorithm to solve a problem is not actually implemented by a programmer. It's not implemented by a software engineer. The data you feed into a machine learning model defines the algorithm to solve that problem. You feed in different data and it solves the problem differently. You feed in more data and it solves it more accurately in certain cases, right? Like you give it some data, hey, this is the input data and I expect that output, and you do that a couple of times and it learns from that input data what output you are expecting. Neural networks is, as you can see, a subset of machine learning, and neural networks is just a way of building a machine learning model that is inspired by the human brain, or a biological brain in general, with neurons, and they are all connected. And deep learning, which surely you have heard, which is one of the most hyped terms in this whole broader topic. Machine learning is a subset of neural networks, of artificial neural networks, which just means that it has particularly many layers of neurons that are connected to each other. And so we've been seeing how these machine learning models fail, and one of the reasons why it fails is that they are just very complex. As you can see here, this is it's actually a very simple deep neural network. In real life, these deep neural networks can have thousands of nodes and 50 or 100 or hundreds of layers. And basically all these nodes do like some small computations, right? And they're connected, and the result goes into some other node, and that result goes into some other node. And there are a lot of them are interconnected. In this case, all of them, they are fully connected. And I think the point here to understand is that these machine learning models that we use nowadays are so complex that it is virtually impossible for a human to understand why things happened in a certain way, why certain input resulted in a certain output, why this model decided this or and not the other way. It's so complicated that we can simply not see that. So that is one of the reasons why machine learning fails. Like you test a lot of cases, but you can never cover all of the cases, right? And there are clearly cases that will fail because you simply couldn't anticipate that the model would react in that way because it's simply too complicated. And let me tell you about this other story, which is a great story from 2011. In 2011, there was the city of Boston. The city of Boston had a problem, and it was potholes. They had too many potholes in the city, and they wanted to find a way to solve that problem. And it was 2011. They did what everyone did in 2011. They built an app. So they built an app for that, and it was actually a pretty smart app. It worked in a way that people would install the app on their phone, then put the phone on the passenger seat of a car, and then they would drive around. And when there was some vibration and the phone noticed there was a bump, it saved the GPS coordinates of where the phone was at that time and sent it to the server of the city of Boston. So then basically the city of Boston could map where all the phones detected potholes and could go and fix them. Now there was one very interesting thing that the people found out, and it looked like only in the areas with the rich people, only in the high cost of living areas were potholes found. And clearly that is a very interesting result, right? Why would only in rich areas be potholes? And so the thing that people didn't think of in the first place was, it was 2011. a smartphone that could install an app was very expensive at that time. Not everyone had a smartphone. It wasn't as ubiquitous as it is now, where every 5-year-old child is watching TikTok videos on their smartphone. 2011 was a different time, and what that meant was only the rich people had the smartphone and installed the app. So the interesting thing here to note is there was no machine learning involved. There was no AI whatsoever, right? The thing that went wrong here was that the data was wrong. The data only came from a certain subset, of the citizens of the city of Boston, and that's what made the data wrong. There were obviously potholes in poor living areas, and they found that later out because they fixed it, which I also have to admit is particularly smart. They put the phone on the app in public buses and on garbage trucks that would basically cover the whole city, and that's when they figured out that there are also obviously potholes in areas with a lower cost of living. But the interesting thing here is to note that there was no machine learning, and yet it failed because the data was wrong. And now let me show you another example. Let's see what happens if I translate the following sentences from English to Malay. Let's say she is a doctor and he is a nurse. And there was something similar happened a couple of years ago and got popular in the Turkish translation. So why I selected Malay here is particularly interesting because Malay does have a gender neutral preposition. So this she and this he that I'm using here in English results in the same word in Malay, right? So that it kind of loses the gender. And now we see how it translates into Malay. And if I now translate this Malay back into English, see what happens. Remember, I wrote she is a doctor and he is a nurse. If I translate that back, if I translate the exact same that we just received by translating it back into English, we get he's a doctor and she is a nurse. Now, how did that happen, right? Like clearly we saw translating it into Malay, the gender information got lost. But yet somehow now it is introduced again, but wrongly. Like we had she is a doctor and all of a sudden it's him. All of a sudden it's he is a doctor. And the reason for that, again, is the historical data that is being used. This Google Translate and other translation service basically read a lot of text. They have text in multiple languages, and they read both of that and then compare, okay, this sentence translates to that, and what they found in the historical text, in the historical data, that doctors were mostly male and nurses are mostly female. And based on that historical data, this is the translation that best fits this Malay sentence. And there's something that we can see that's clearly a sexist approach. Right nowadays, we know that there's no reason why a woman can't be a doctor or a man can't be a nurse. But I think that again shows how, even though there is machine learning, this particular issue is based on the faulty data to begin with. And it was discussed some time ago, a couple of years. It came public when the same issue was found in Turkish because there's the same genderless pronouns. And what Google introduced then was they knew about that issue and they introduced both gender options to show. Right. Let's talk about some other issues with data, right? There's the compass system. You have probably not heard of it unless you are in the US and might have been to court. This compass system is used in the US American jurisdiction, and it is as it says, a correctional offender management profiling for alternative sanctions system. It basically, what it does is people who've committed a crime fill out a form, like 200 something questions, and based on how they fill out that form, this computer system predicts whether they will commit a crime again or not. And based on that outcome, the bail that they have to pay and the time they are going to spend in jail is adjusted to that. So if a judge sees, oh, it's very likely that that person commits a crime again, they the sentence that they speak will be higher than if the system would have said, this is a very clean guy, he won't commit a crime again. And obviously that fails, right? If we look here at the number of people that were labeled a higher risk but did not reoffend. So that is the false positive, false negative, or however you want, right? You can see that only affected 23%. 23% of the white people got labeled higher risk and did not do anything. But almost 45% of African Americans got labeled a higher risk and did not reoffend. And if you turn it around, people who got estimated to have lower risk of reoffending but then did actually commit a crime again, that is particularly true. There's almost 50% for white people, and for African Americans only 28%. So what this means is that the data that is being put into that system, and there are very generic questions. There are questions that are about the neighborhood you live in. There are questions about your parents and so on. Based on that, and there's no information about whether people are Caucasian or African American, right? But based on the data that is put in, the system has a clearly a racist position against black people, where it is significantly higher percentage of labeling them as a higher reoffending chance. And the same thing, the opposite is the case if you are white. And this system is still being used, and this analysis was done by ProPublica, and they that is very interesting, since there was no in this questionnaire, there was no mentioning of your skin color or your ethnicity whatsoever, but based on other aspects, the pseudo-identifiers in a way the system figured out, okay, this is a black person, and then discriminated against them. And that is still being in use nowadays. And there are a couple of other situations. There's a study, as you can read here, that found out that self-driving cars have a higher risk of failing to detect dark-skinned pedestrians. And what that means is there's a car driving, self-driving, right? No driver. And what it's doing is have a couple of cameras, right? And LiDAR radars around to identify the environment, to not run into people. And these systems have a lower chance of registering dark-skinned people as pedestrians. That means if there is a white person, it is more likely to be identified and not being driven over, where if it's a dark-skinned person, there is a higher chance that the person gets not identified as a pedestrian and gets potentially killed. And I think that is, again, the reason for that is most likely that the data that was used to train those models, to train the image recognition, was mostly white-skinned people, and therefore it was not trained to identify dark-skinned pedestrians. And that is just, that will kill people if that gets widely deployed. So basically, if you feed bad data into a machine learning model, it will react in a certain way. Right, and now you're looking at me saying, Aiko, you're telling us machine learning sucks, machine learning is everywhere, the world is on fire, are we all doomed? And I can tell you we are not. But there are a couple of things that we need to do. And when we decide on what machine learning model we want to use, we want to follow a couple of criteria. And explainability as a first-class model selection criteria is one of them. That means we need to understand why a model is decided in a certain way. For this particular case of convolutional neural networks, which is mostly used for image recognition, you can see here on the bottom, there is each layer, there's a form of visualization that lets you see what each layer is deciding on, what each layer is recognizing, and then making a decision based on that. In the other way expressed, what we need to change from our standard ML approach to an approach where we use interpretability and feed that into the model and then train the model again. There's a technique that I really like, which is called LIME, which stands for Local Interpretable Model Agnostic Explanations. And what this does is it basically looks at your model, and it is model agnostic. It goes for various machine learning models. It goes for neural networks, and what it does is it tries to explain why things happen. And if we take, for example, this image recognition, where the image that we can see on the left was taken, and it was identified as a tree frog with a 54% score. And what this LIME then does is, and this is a nice visualization, it takes away certain data from the trainings data set, from the test data, and then see what the model does predict. And what that means is you just throw out some data, and if it still predicts the same thing, you know the data that you threw out is irrelevant, right? The data that you kept is relevant, and you can see here on the frog, you keep the eyes and you keep the green face, and that is the relevant part. And if you see in the middle page, you keep the background, that is irrelevant for the prediction of this image. Another thing is we need more diverse teams. We need to have a different perspective on things, right? If you remember the autonomous driving cars, if there were higher diversity in the team, maybe they would have tested for dark-skinned pedestrians on the pedestrian recognition system. Another thing that I really like is there's this data ethics canvas, which gets published by the Open Data Institute, and it basically lets you ask a couple of questions. Like, it has a list of questions, and before you start defining what model you want to use, you have to ask yourself these questions, like who you share the data with, what are the limitations of your data sources, and so on. Basically a list that you can go through and see what you need to do. Sometimes you need to remove data. Do you really need, like, if you have racial data in your data set and you try to predict something where you don't need that information, should you just keep it in? Maybe just throw it out, right? It could, if you don't need that data, you can throw it out before it starts affecting your result. There's this other thing that I really like, which is open source visualization tool from Google, which is Facets, where you can just feed in data and you can just select certain subsets, and you can see, in this case, for example, 85% of my participants in that data were male. So clearly your data is skewed into that male category, and you have underrepresented females, for example, or other genders. And a similar thing is the what if tool, which lets you compare multiple models with the same workflow and integrates well with the facets system that I just showed you. And it lets you inspect a little bit how your model would react in certain ways. Yes. So I hope I could show you that there are a couple of issues with using machine learning, widespread machine learning algorithms, basically based on two things. Number one is that if you don't pay attention, you basically have a black box and you don't know how your machine learning model reacts. And in addition to that, that your data might be skewed, and if you don't figure out the where your data is lacking and what underrepresented groups you have, you might end up with wrong data. But I hope I also showed you that there are certain ways how to fix those problems. And with that being said, thanks for your attention, and let me know your questions.